All right, y'all. Let's do it. So the last unit that we are going to cover is basically like waves and optics. So we're going to cover two things today. The first thing we're going to cover is kind of a general overview of electromagnetic waves. The second thing that we will cover is going to be what we call geometric optics. So when you look at optics, we tend to break it down into two categories. There's, Avi, if you keep talking, it's going to show up in the video, so go talk somewhere else. Legitimately, if you want to go, like, leave the room, it's fine, but don't talk. So when we look at optics, there are two categories. There's geometric optics, and there is physical optics. Geometric optics, y'all should be at this point familiar with the idea of like wave-particle duality, right? Like that's a thing that you've learned about in middle school or something, yes? Maybe? So, in general, geometric optics is going to be optics that are designed to take advantage of the particle behavior. And so it will tend to treat things, treat light as rays. In other words, you can think of it almost like as beams of particles. So some optics are designed to take advantage of those aspects. And then there's a whole other area called physical optics, which is designed to take advantage of the wave behavior of optics. And so those are the last couple things to cover. Today we're going to do generally, here is what light is, as well as geometric optics. And then tomorrow I'll cover physical optics, which is actually not a ton for y'all to understand there. I think we'll talk about polarization and we'll talk about the double slit experiment. I think that's really about it. And then we'll be done. So we should be done end of day tomorrow and have Wednesday, Thursday, Friday to, just have parties or take naps or whatever. Yeah.
I'm supposed to leave to go to the dentist, but they haven't called me and I don't want to be late, so
It's good.
I'm gonna be
Just make sure you check it on the way out.
I will.
True. They'll get on to you for that.
They will get me.
All right. So let's get into it. By the way, this says light in the Doppler effect. I'm going to say the Doppler effect for tomorrow, so we'll hang on that one. All right. Electromagnetic waves. So here's the deal. Electromagnetic waves are called electromagnetic waves because they are both electric and magnetic waves, right?
Wow.
Crazy.
That's crazy.
So, if you look at this picture here, what this is trying to show you is that this is a traveling oscillation. That's what a wave is. You should remember that from talking about it last year. Wait, did we cover waves last year?
No.
AP1 cuts that out, don't they? Oh boy. Okay, so waves, I was not prepared to teach you this part, are traveling oscillations. Okay? Hold on, I've got like a whole thing for this. Come here, big springs. Ah.
Did I have one?
Oh, jeez.
Why are all these jacked up?
Oh my god.
No. Alright, this might be the best it's gonna get. I need a volunteer.
I'll do it.
Come here.
Hold on, wait. I'm a little scared.
Catch. You gotta catch. You gotta catch it.
Okay,
You
don't
gotta
be a
catch
hater.
it. I'm not being a hater. No, we gotta pull it tight, which I think is, you have to pull it fairly tight here. Alright, so look. Traveling oscillation. In a moment, I'm gonna move my hand up and down. Just whoop. And what you'll see is that up-down motion will travel through the spring. You ready? Did you see? Right? The spring does what the hand does. So if I do this oscillation, that oscillation travels through. If I keep doing it, it'll keep going through. Oh, and look, we made a standing wave. Look at that. That's a special fun thing. Okay, so there are two types of waves. Actually, there's a lot of types. There are two general categories. One is a transverse wave, which is what I just showed you. If I move it, it's going to move down the string, but the motion is perpendicular to the spring. You see that? Like watch the oscillation, and you'll see that it moves down the spring, but the motion is up and down, right? The other one you can see is a transverse wave. A transverse wave is one that travels in the same direction as the wave, like this. This one's harder to see. You see it? So if you could like pick a coil, you could watch that one coil oscillate. Important to see here that the spring is not moving, it's just oscillating, right? Each individual coil is not moving, it's just oscillating. So this is what a wave is. And like everything that you hear are sound waves. Sound waves are longitudinal waves, waves like this one. And they're compression waves. So the pressure in the air is changing. And then we have, these little drums in our ear that pick up on those pressure changes. And that's how you hear things. We're not concerned with physical waves, though. We're concerned with light waves. So let's talk about those. But at least that gives you a little background. So now if we go back to this slide, you can see that there is the blue here is an oscillation in the electric field. So the electric field strength is going up and down. Notice that it's also oscillating between positive and negative. The magnetic field strength is also going up and down. And so what we're looking at here when we look at electromagnetic waves is a traveling oscillation of the electromagnetic field. And that's what light is. Okay? That is at least the wave nature of light, is that it's an oscillation in the electromagnetic field. Does that make sense? Mm-hmm. Okay. Now, what's interesting about this is that when I made the waves in the spring, that spring had to be there to move. And you may be familiar with this idea that if you go out into like space, there's no sound in space. Are you all familiar with this? Mm-hmm. The reason for that is because there's no particles to oscillate, right? So if you are sitting in a spacesuit screaming, no one around you will hear you screaming because there's no particles to pass in between. That's why sometimes in like sci-fi movies, at least the good ones, you'll see that they'll like, if their comms are out, they'll come like touch helmets together and then they'll talk because the vibrations will travel through one helmet and into the other, but they have to be physically touching for that to happen. So physical waves require a medium in order to move, all of them. Electromagnetic waves do not. Because they're not oscillations in matter, they're oscillations in a field. And that means that they can travel through anything. It also means that they can travel as fast as the universe will let them, which is why the speed of light is c, the speed of causality. We don't have time to go into all that. That would have been a fun nuclear quantum relativistic conversation. But the point is, there's only so quickly one thing in the universe can affect something else in the universe, and we call that speed the speed of causality, and that's how fast light moves. That's why the constant for it in all the equations is c. It's because it's the speed of causality. I had another thought, but then it ran away. Oh, while we're on the note about speed, the speed of light literally never changes, ever. However, the speed of light as it travels through materials is apparently slower than when it travels through vacuum. I say apparently because it's important to understand that the light itself always travels the same speed. But when it's passing through a material, what happens is basically that the light gets absorbed and then re-emitted as it travels through the material. And because it's absorbed and re-emitted, it's almost like there are little pit stops along the way. So between any two molecules, the speed of light is the same, but because it's being absorbed and re-emitted repeatedly, it kind of slows it down just a little bit. So like the speed of light through air is essentially the same as vacuum, but slightly slower. The speed of light through water is a little bit slower than that. This is why we get some weird things that happen called refraction, which we'll talk about later. Does that make any sense? I know it's a bit weird. In fact, like, fun, weird thing, when the window's not open so you can't see, but like, when you look at the window, you're not seeing the light from outside. What you're actually seeing is, what happens is the molecules that make up the glass absorb the light and then perfectly re-emit that light on the other side. Does that make any sense? Which is why there's a slight energy loss, right? That's why it feels slightly less warm than if you're outside, is because of slight energy loss. So some materials are really good at transmitting those wavelengths essentially exactly as they came in. Typically that's because they have a really large emission spectra, so silicates are fun for that, which is why glass works. Anyways, not why we're here. Let's move on. I'm going to be a little random today because my brain is hurting me. All right, so let's talk about the electromagnetic spectrum. So you probably hear the term radiation a lot. Like I watched a bunch of Godzilla movies this weekend because I was holding my kids and couldn't do anything. So, which by the way, like super hilarious life moment here. I'm sitting on the couch. I'm holding Peter while he's taking a nap, and I'm watching the second of the most recent Godzilla movies. So Godzilla is fighting King Ghidorah, like in the snow, I guess, but they're fighting, right? It's like the monsters are fighting. Macy walks in, looks up at the screen, sees the monsters like shooting lasers at each other and stuff, right? And then she turns to me and she goes, "Is this a Christmas movie?" And I was like, no, it's not. I guess she saw the snow, I don't know. Maybe she just thinks everything's a Christmas movie right now. Anyways. So when you look at the electromagnetic spectrum, oh yeah, radiation's what got me off on that trail. So radiation is just any sort of electromagnetic radiation. That's all it is. Now we'll talk about there's some radiation that's dangerous. There's some radiation that's not. And so what I want to camp out here real quick is just to talk about the spectrum just a little tiny bit. And then we'll move on to the first of the geometric optics topics to talk about. So we can see that like you've got light from big waves to small waves. What we mean by big waves is the length of the wave, right? So when you look at things like radio waves, the wavelength is really large. Those are very low energy waves. Okay, they don't carry a ton of energy, but they can travel for a long time without degrading. Okay, so radio waves are way over here. We use those for communication. You should be familiar with all those types of things. I want you to see that as we keep moving up, we get into the microwave range. Now, side note, all of the dangerous radiation is the high energy radiation over here. Okay? Notice that microwaves are over here. So, despite what you may think, microwaves are not dangerous. I think I've told you guys about this before, but if you were to like put your hand in the microwave, you would just get cooked, right? There's this misunderstanding that microwaves cause cancer. In no way, shape, or form do microwaves cause cancer. It's scientifically impossible for them to do that. You should be more worried about the plastic you're putting inside the microwave than the microwave itself, because the plastic you're putting in there probably is giving you cancer. You should stop microwaving plastics. Even if they say microwave safe, they're not. Don't do it.
Like Tesla.
Yeah, don't put those in the microwave.
What about plates?
Plastic plates?
I don't know.
Don't put plastic. Don't put plastic in the microwave.
Well, plastic,
Period.
plastic.
I think that's
Plastic.
just generally, don't put plastic in the microwave. Hey, let me let you know on a secret, okay? Plastic is giving everybody cancer. It's terrible. Stop using plastic in general, but definitely don't put it in the microwave. Like seriously, if no one's told you this yet, plastic is a huge problem.
Good job. Wow.
It's that too. It turns out plastic was this like miracle thing that we discovered, and then we were like, all right, this thing's super cool. Let's use it for everything. And then like it's been like what 50, 60 years later. It's like, oh wait, this is actually like destroying the planet and our bodies, and now it's too late to fix. Classic human behavior, you know. But it's not too late to start cutting back. Anyways. Microwaves. So how do microwaves cook food if they're not high energy? Well, the short answer is that what they do is they jiggle water molecules at the perfect frequency to make them kind of like spin, and that heats up the food. So it's just like a resonance thing, not a high energy thing. Anyways, we get up here, we get into, oh, by the way, microwaves are also used for lots of other things, like radar is a microwave. That's how they do, like the cruise control on your car that can see the car in front of you. That's microwaves. So microwaves are used for a lot of different things. There's just like that perfect little wavelength that resonates with water molecules. So then you've got infrared. Infrared is the light just below the visible spectrum. Lots of things emit infrared, which makes it really useful for like night vision and that type of thing. Then you get into the visible light. So the visible light, red, orange, yellow, green, blue, purple. Which, by the way, minor pet peeve. When you look at the rainbow doesn't have every conceivable color. And the reason for that...
Boston,
Yeah?
Paul Lieber to the front office.
Yeah. The reason for that is because the rainbow is made up of all of the individual color photons. But that's not how our eyes perceive light. Our eyes perceive light based on all sorts of things, right? And so that's why there's no brown in the rainbow. There's no pink in the rainbow. That doesn't mean they're not colors. People say that all the time. I just want to punch them in the face. They're just not in the rainbow because they're not pure photons of light. Does that make any sense? Like if you didn't know this, which I think everybody does at this point because it hit TikTok a while back, brown is just a low intensity orange, in other words, a dark orange, right? Pink is what happens when your eyes are seeing both purple and red at the same time. Our eyes interpret things weirdly because of the way that they're designed. Let's just leave it at that. Okay. So there are lots of colors that we see visually that are not in the rainbow, and that's okay. All right. Once you get above that, we start getting into like a little bit of the danger zone. So ultraviolet light. Ultraviolet light is higher energy. It's not yet what we would call ionizing energy. So ionizing energy is where it will hit a molecule and cause it to ionize, which obviously makes that molecule work completely differently. So imagine if I start ionizing the molecules in your DNA, what do you think is going to happen?
We're going to start
Probably not, because you're not a lizard. What?
Will start working differently.
It'll start working differently, and that probably doesn't lead to good things, right? That's why we start getting cancer development when we look at exposure to this higher level of radiation, is because it's ionizing your cells, and a part of that is that it can lead to, either because your cell replicating materials are damaged or your DNA itself is damaged, it can lead to DNA issues and therefore cancer. So that doesn't start until about UVC though. So UVA and UVB will give you sunburns, but that's a whole other story about how that relates to skin cancer. We're not here for that. So UVA and UVB, not great for your skin, but doesn't really ionize. And then UVC and above, that's where we start seeing energy high enough to ionize. Now look at this. We're pretty lucky because the sun is creating all of this light all the time. But we've got a magnetosphere and we have an atmosphere that filter out a whole bunch of this stuff. So I want you to notice that like a whole bunch of this not so good stuff is filtered out through the atmosphere. So it never hits us, right? This is why everybody was freaking out about the ozone layer a while ago. Y'all remember that? Everybody was like, oh no, the ozone is everybody in Australia is going to die. And then we got better at making materials and it's fine now. But that's because that part that was filtering out a lot of this stuff was going away. And so we were concerned there was going to be a higher concentration of that light coming through and giving people more skin cancer. Anyways, point being, upper level, that's where you start to have issues, okay? By the way, other fun thing, X-rays and gamma rays, they're actually essentially the same from a light perspective. The only distinction is how they're produced. So X-rays are produced when an electron jumps down an energy level, okay? Gamma rays are produced when a nucleus breaks apart. So they're almost identical, at least for a certain band, but they're differentiated by how they're produced. Point being, here's all the light. When you hear people say radiation, don't freak out unless they're talking about UVC, X-rays, or gamma rays. That's where you start to have issues. Does that make any sense? Questions, comments, concerns, complaints? All right. We're not going to do either of these things. So there's at least an introduction into what that looks like. So for today, my only other goal is to cover geometric optics. And really here, it's not even all of geometric optics. I'm looking to cover mirrors and lenses. And then tomorrow we can go over 3 topics, one of which will still be geometric, which are refraction. Well, yeah. We'll cover refraction. We'll cover the Doppler effect. We might cover polarization. We'll definitely cover double slit. All right. So, don't need that. So before we get into anything else, let's talk about how light is produced or reflected. So for this conversation, we're talking about geometric optics, so we're going to consider only materials, or we're going to consider light only as existing in beams or rays, right? So it's like, there it goes. We're ignoring all of its wave-like properties. We're only going to think of it as beams of particles. Does that make any sense? Mm-hmm. Okay. So then when we talk about light being produced, there are two different types of objects. One is self-luminous objects, which are objects that make their own light. Okay, those are things like the sun, the light bulbs in this room, this laser pointer. Anything that actually produces light is self-luminous, and then we have reflective, which is everything else. So everything else that you can see is because it's reflecting light back at you. Okay? And y'all probably at some point had a teacher explain to you that the reason different things look different colors is because they're absorbing the other colors and they're reflecting only the color you see. Y'all been taught that before? Mm-hmm. Okay. All right, which is why black things get hot when they're out in the sun more. They're absorbing more of the light, right? They're not reflecting as much. We also need to talk about the term image. So objects will either produce light or reflect light. Images are light that our eye perceives that are not actually because a physical object exists. Does that make any sense? So like right now I'm looking at you through glasses, and so what I'm really seeing are images produced by the glasses, not actually your actual bodies. So, a virtual image is an image that's created when light does not actually pass through an image point. This may seem weird in a minute. You'll see why we have this distinction later. A real image is where light actually passes through the image point. What's interesting about this is that means that I could take a piece of paper and stick it where the image is being created. If it's a real image, it will show up on the paper. If it's a virtual image, it will not. Does that make any sense? So real images, the light is actually converging at that point. For virtual images, the light is appearing to converge at that point, even though it doesn't. Does that make any sense? Mm-hmm. Yeah, you've been listening the whole time. Great job. Yeah. All right, so let's start our discussion with plane mirrors. So let's say I have just a simple object that's a single point. Well, we would think of this object, whether it's self-luminous or reflective, what's happening is that there's light being scattered away from it in every direction like this. We cool with that? There's light coming away from it in every direction. Now when these light rays hit this surface, they're going to reflect off of that surface following what's called the law of reflection. The law of reflection is that the incident angle is equal to the reflected angle as measured from normal. What does normal mean? I'm glad all of you guys are paying attention.
Typical. Average.
Do you remember the normal force?
Yes.
Which way did the normal force point?
Perpendicular.
Perpendicular. So the word normal mathematically means perpendicular. So we're looking at all of these rays will reflect at the same angle they came in at as measured from perpendicular. So that means they would look like this. You cool with that? Now here's the deal. If you're looking at this mirror, the light hits it, it scatters everywhere, right? And it scatters following this law. But our eyes are clever, and our eyes catch all that light, and they're like, you know what? I think I can imagine a point where that light converges. So if you trace the rays back into like the mirror dimension on the other side of the mirror, then you would see, look, all those light rays, they converge at that point. We call that the image point. Okay? This is a virtual image. Our eyes think that the light is converging at a certain point, but they're not really converging. Does that make any sense? Virtual image. So when we look at plane mirrors, what we see are that those mirrors always produce virtual images. Y'all are familiar with these, right? You've seen them. And they basically produce, we call them mirror images, right? Y'all are familiar with these. They're not super exciting. If I take this idea and I deal with a two-dimensional object, you can see here, I've got orange up top, gray down bottom, and you can see the rays that go in and reflect. So if you have a two-dimensional object, you just do it at two different points, and you draw the ray diagram and you see what happens, and you can see, look, the lamp is reflected, right? All right, so the more interesting thing are what we call spherical mirrors. These are mirrors that are curved. Not all curved mirrors are spherical mirrors, but we're going to talk specifically about spherical ones. So there are two types of spherical mirrors you'll see, concave and convex. Concave is the one that you look at it and it looks like a cave. Convex, it looks like a vex, you know?
Are the convex mirrors like the one that you see in like the corners of hallways? You can see like...
Yeah, they are, 100%. Okay, so we're going to talk about each of those quickly here. Some terms that you need to know before we talk about that though. So, you've got this point C is the center of curvature. So if you can imagine this spherical mirror continues all the way around that center of curvature. The focus is where light will focus, but geometrically it is halfway between the center and the actual outside or the lens. Does that make sense? Mm-hmm. And then you have the vertex, which is the point that we're looking at where it's like touching the mirror. Okay. Cool? All right. So one of the things that we can do to understand what's going to happen with these mirrors is we can draw ray diagrams. And so what we're going to do is we're going to draw two rays. One is that basically we're going to take this idea where if you analyze this, I'm not going to do the geometry for you, but if you analyze a sphere and apply the law of reflection to it, what you would see is that any light that comes in parallel is going to parallel to that optical axis, which is that dashed line. Anything that comes in parallel to that, it's going to hit the mirror, and it's going to reflect back through the focus. And again, this is just geometry that I'm not showing you. On the other end, if light travels through the focus, it will reflect back parallel. Does that make any sense? So I'm going to take advantage of, I know how a parallel light beam behaves, and I know how a light beam coming to the focus behaves. I'm going to use that to see where the image is formed. So I'm going to draw one line that's parallel, and then bounces back to the focus, and one that goes through the focus, and then bounces back parallel. Yes?
So you might have already covered this, and it's kind of stupid, but if you had a perfect sphere and the inside of the sphere this mirror and it was somehow like permeable to light, what would be in there? Like,
There's a Vsauce video
Well,
about that.
what you just described is an impossible situation.
There's a
so.
Vsauce video about it.
well, Vsauce made a video about it, so possible.